Hi, my name is Sam, and I'm excited to be presenting virtually with my teammates Adarsh and Sarah to tell you about MARV, the Maritime Autonomous Rescue Vehicle. With the Artemis program, NASA is entering the next generation of space exploration. By 2024, NASA will have begun sending yearly personed missions to the Moon. These missions will serve as stepping stones for further missions to deep space, Mars, and beyond. But with this added traffic comes added risk. As they prepare for the next generation of space exploration, NASA must also prepare for the next generation of search and rescue. In the event of failure during or after launch, the Orion capsule will propel into the ocean off the coast of Florida. At this point, it is essential that all astronauts leave the damaged capsule immediately. To do so, they will attempt to enter a life raft, which they have now thrown from the capsule. Now, the astronauts must activate the SARSAT beacons on their suits and wait for first responders to arrive. So, what happens if an astronaut is separated and doesn't make it onto the raft? The truth is, nothing different. A contingency landing is a catastrophic, sudden, and dangerous event, and such an escape can be difficult. In the event that an astronaut does not make it into the raft, they could be left alone in the ocean for a period of many hours, drifting farther away from the main group. Search and rescue is designed for the most efficient allocation of resources, and the main life raft will be attended to first. This is where MARV comes in. MARV can be quickly deployed from a helicopter or Class 2 UAV. Once in the water, MARV begins to autonomously approach the stranded astronaut using a combination of GPS navigation, beacon signal tracking, and visual recognition. MARV then remains with the stranded astronaut until first responders can be deployed, which, as we said, can be a period of hours. MARV delivers with it a payload of rescue aid, including a liter of fresh water, a spare life preserver unit, a spare beacon, a medical kit, and a survival radio. Now, the stranded astronaut is directly connected to NASA personnel via the survival radio and the precise GPS location of MARV. Now, what are the constraints for MARV to accomplish this mission? Class 2 UAVs have a weight limit of 55 pounds. Thus, MARV needs to be within this limit in order to be deployed. MARV must also be capable of surviving the 15-foot drop from the UAV or helicopter into the ocean, and function regardless of landing orientation. After this drop, MARV must remain completely watertight, ensuring the safety of MARV's electronics. Once in the water, MARV needs to approach the astronaut, and needs to maintain 3.5 miles per hour for an hour to do so. MARV needs to carry with it the 6.5-pound payload of rescue supplies, and must do the entire mission autonomously. And with that, I'll pass it on to Sarah to talk about the design and engineering efforts that went into the creation of MARV.
Thanks, Sam. One of the biggest early decisions that we made in designing MARV was whether to design a monohull craft or a catamaran. After doing some research into both hull types, we developed a list of pros and cons. The main attractive aspect of the monohull was that there would only be one hull to manufacture, which would be less weight overall. However, we learned that self-righting would be near impossible, since at this scale there is not a large enough moment arm to be generated. Conversely, with a catamaran there are two stable configurations, which ensures that the boat will either settle right side up or be inverted in the water. Potential drawbacks, however, included more manufacturing overall, increased weight, and the need for multiple propulsion units. However, given that the monohull option cannot self-right, we ultimately selected the catamaran design. Moving on to the propulsion system selection, we weighed both jet drives and propellers. Jet drives have the benefits of being safer for the astronauts and potentially being more impact resistant, which is a concern given our 15-foot drop constraint. However, after researching jet drives, we found that we would have to incorporate intake valves into the design, which would create additional waterproofing concerns and complexity. On the other hand, propellers were much more economically feasible. They also would have been less weight per unit added to the vehicle. However, the main concern with propellers is that the astronauts' fingers or tethers off of their suit could enter them, which would be a safety hazard. Ultimately, we chose to use the propellers for MARV with plans to develop ways to mitigate these tangle and impact hazards. To create our final prototype of MARV that would meet all of the constraints and characteristics necessary to achieving its mission, we developed two previous versions of MARV that would help us get to MARV's final form. The first prototype being a quick and dirty way to gather data of the 15-foot drop to be later used for ANSYS in our design process. We quickly built a boat of the estimated size and shape of MARV, got it up to the 55 pounds, attached an inertial measurement unit in a waterproof box, and dropped it. What we found from the tests was that the maximum boat experience was around 3,700 newtons. Qualitative observations also confirmed significant bending in the center structure as well as torsion and issues with the interface between the hull and the center structure. And now I will pass it back to Sam to continue to discuss our design decisions.
Thanks, Sarah. So with the knowledge we gained from this first prototype, we were able to select the correct hull material to satisfy MARV's design constraints. The need to survive a drop eliminated weaker materials, such as woods, ceramics, and foams. Materials such as metals, although strong, required a large amount of weight to be added to the hulls. Plastics were also eliminated, as they would be difficult to manufacture due to the unique geometry required by MARV. The choice then became between carbon fiber and fiberglass. Although fiberglass required a small amount of additional weight to reach our desired hull strength, it came at a much lower cost than carbon fiber, and still allowed MARV to satisfy all constraints. Next, we used our drop test data to determine the necessary strength of our center structure. To do so, we began by idealizing our center structure as a beam. This necessary strength was then translated into a materials index, allowing materials with similar properties to be compared. Due to the manufacturing constraints, a metal was chosen, and two options, aluminum and titanium alloys, were compared. Aluminum was chosen for its lower cost and greater manufacturability. We then validated the design using FEA before having it professionally welded. Many further design decisions had to be made in the creation of MARV, and many of these decisions were complexly interrelated. To find the ideal configuration of size, battery power, hull thickness, and more, we created a detailed Simulink for design space optimization. This Simulink stepped through many iterations of empirical hull slamming modeling, hull weight approximations, drag estimations, and battery calculations to output estimates of MARV's maximum stress during impact, draft height, cruising velocity, and battery lifespan. By filtering out the configurations that did not satisfy our physical constraints and manufacturing capabilities, we were able to identify 15 configurations from the 50,000 originals, which satisfied our needs. With this knowledge, we were able to create a high-fidelity second prototype. This prototype included laid-up fiberglass hulls, a welded aluminum center structure, our 3D printed thruster guards, and a basic electronics package. With this prototype, we were able to perform both drop testing as well as controllability testing. We were excited to see that our prototype did, in fact, survive multiple drops from different orientations into the Schuylkill River. We did see, however, some issues with water tightness, which were tackled in our final prototype. We verified the controllability of MARV with our pool test, as well as confirmed our estimates for drag coefficient. We were also pleasantly surprised to find that MARV was even strong enough to pull a person. With the knowledge from our second prototype, we were able to finalize a design for our final prototype, capable of carrying our full electronics package and payload. This prototype also included a new subsystem capable of rotating MARV's antennas upon landing. And with that, I will now pass it on to Adarsh to dive into the details of MARV's final form.
Thanks, Sam. So with everything we've learned about our first two prototypes and design considerations from Sam and Sarah, let's talk about the final prototype. The big changes between prototype 2 and prototype 3 were first, a much more streamlined manufacturing process. This resulted in a significant decrease in excess weight in the hulls and center structure, as well as much more watertight interfaces between the two. Prototype 3 also brought with it a complete electronic subsystem, as well as the addition of the antenna rotation subsystem. This is critical because we want to make sure MARV's direction-finding antennas are operating in the correct orientation no matter which way MARV lands. To go into more detail about our electronic subsystem, let's start with the compute box. This device contains both of our computers, including a Jetson Nano as well as an Arduino Uno. We also have a couple of different cameras, both visual and thermal, as well as two different radios, one for direction finding and one for general communications. We also have a combination of different antennas, as well as a number of other spatial sensors like GPS and compass. Our second electronics box is our battery box. This contains a 240 watt-hour lithium polymer battery. It also contains 4 electronic speed controllers, as well as a 5-volt regulator and other supporting electronics. This also contains domain switches and safety electronics in order to turn MARV on and off. We have a lot of different electronics in these two boxes, and where each piece went was very, very deliberate. There were 3 main design constraints we kept in mind when deciding where to put what. The first one was heat dissipation. What makes these electronic boxes so great from a waterproof perspective makes them pretty terrible from a heat dissipation perspective. So it was critical that we made sure that we were getting rid of all that heat in a responsible manner. Second, that force felt by the rest of our boat is also felt by the electronics on impact during the drop. So it's critical that we make sure that we don't have any wiggly connections and then all the electronics are quite shock resistant. Finally, we have some visible sensors on board MARV, so we have to make sure that based on their mounting points in the boxes, they are maintaining the observability they need to operate properly. Given all of the electronics we've got on board MARV, our software infrastructure was critical. Basically, the way we went about this was we have a number of different sensors that are input to the robot operating system, that's ROS. ROS lives on the NVIDIA Jetson Nano, where all of our computation is happening. So that's our state estimation, sensor fusion, planning, and other control algorithms. Once we have those control values, we send them down to the thrusters and the loop repeats. To go into more detail on the specific pieces of software we've got, the most important one is the mission manager. That's a robust state machine that knows at any given time what mode MARV is in. Are we still in the helicopter, or are we already navigating via beacon tracking? There are 3 other supporting nodes that are shown above the mission manager that allow for control of the thrusters, knowing where in the world MARV is, as well as monitoring the orientation. The third category of software we've got at the bottom is all of our goal-based planning behaviors. MARV's planner can take in a GPS-based goal, a beacon tracking-based goal, and a visual-based goal, and it's able to operate seamlessly between the 3. With all of these different software and hardware components, it's critical that we have a robust testing plan. First, we did individual component testing, making sure that everything is compatible with everything else. Second, we did a bench integration test, making sure, for example, the digital compass is able to talk to the Arduino, which is able to talk to the Nano. Finally, we were able to do much more extensive integration tests with all the electronics in the enclosure. So for example, the screenshot here shows the thermal camera publishing to ROS, being subscribed to by a different software process for object detection, which is then parsing the output of that algorithm and then being able to publish out controls. So a pretty extensive integration test. At the time that work on MARV was stopped, we were only 2 days away from full integration testing. The other key category of testing we had to do on these boxes was making sure everything was watertight. We purchased a lot of off-the-shelf IP68 components, but we didn't take anybody's word for it. We verified our antenna pass-through connectors, our cable pass-through connectors, and our watertight lids. At any given point in time, we had to make sure that no matter what we added, the boxes remained waterproof. This was very meticulous and allowed us to be confident when we finally did put all these electronics in the boxes. With that, I'm going to pass it back to Sarah to talk more about our user interfaces.
Thanks, Adarsh. Another important consideration in developing MARV was the incorporation of features to ensure the seamless and intuitive use of MARV for both the search and rescue personnel and the astronaut. This included handles and live communication with the search and rescue team to easily deploy and track MARV's location. And for the stranded astronaut, we needed to make MARV easily visible, hence the orange color of the boat, and lead the astronaut to an easily accessible payload box using externally mounted lights. And again, we included those propeller guards to ensure that the astronaut would not be injured during its use. Obviously, given the circumstances of the world right now, we were unable to finish MARV. While MARV's physical construction was mostly completed, save 1 day of final integration, we had plans to further test and validate our vehicle. The first of these being a final drop and pull test to ensure the survivability of the final iteration and to fine-tune our controls. The next groups of tests being a GPS and beacon tracking test, which we plan to perform in the Schuylkill River, and finally, a full scenario test, which would have been from beginning to end, drop to finding the astronaut. While we were disappointed to not being able to fully complete MARV, we are proud of what we have accomplished. We developed a quick prototype to collect data, we performed our first team fiberglass layup and made strides in our electrical work, and we created our final prototype, which was the culmination of all the lessons we had learned. Had we had the time we had lost, MARV would have been a tool in NASA's search and rescue arsenal that would have ensured that no astronaut would be left stranded in the case of emergency. Although we didn't reach the goal, we are very proud of what we accomplished. And with that, we would like to thank our faculty advisors, Dr. Bruce Coatman and Dr. Graham Wabashetti, as well as our external advisors at NASA, Buffalo Automation, Lehigh University, and the MIT Marine Robotics Group. And we would love to thank the internal help we received at Penn, as well as our TAs, Jonah, Mia, and Ali. Thank you for your attention, and we look forward to answering your questions in a later Q&A session.